Hello, everybody online. I hope you're having a fabulous day. I have some students who I'm covering. So give me just a second. I have to make an attendance sheet for them and I'll be right with you. So you guys are going to put your full name and your student ID number. And then last person who gets it, just give it to me so I can give it to Mrs. Knight. So that way you're not marked absent. And William, let me give you your test back. Yeah. There we go. Oh, I brought it to you. Thank you. Okay. So how you guys online doing today? You doing okay?
Good.
Yeah?
I'm good, Miss Wilson.
It's Monday.
I know. 4 more days. 4 more days. Oh my goodness, you guys. All right. So we took a test. You guys did not do bad. In fact, most BC kids rocked it. There were a few who didn't. And the observations that I made are that some of you, I understand, you want to get the problem done, but if you don't use proper mathematical notation, you're going to lose a lot of points on the AP exam. They're very, very adamant, and so is any college level math course, about you using proper notation. And I'll show you what let me unshare this and I'll share my iPad. I'm going to show you what I mean by that, because it's super important. And, I don't know if you're going to have a teacher next week or not. I don't know what the deal is. Have you guys heard anything? Has anybody heard anything that once I leave? Anything?
No, not really.
Okay, well, that's not what I want. I want good notes. I want good notes. Here we go. So what I'm seeing is, number one, you're not writing down the original problem, and you need to do that. So, I don't know, if f of x is equal to 2x cubed minus 6x or something, right? I don't see this. That's problem number one. The other problem is, somewhere over here, I see this. Somewhere over here, I see this. Somewhere over here, I see this. That's bad. This is really bad. And what I'm going to tell you right now is that when you take the AP exam, you're not going to get any points at all for this. All right. What they need to see and what you need to start improving upon is you write down the original function and then you tell the grader, the derivative of this is 6x squared minus 6. And they understand, thank you. They understand that you're using the power rule there, so it's no big deal. If you're doing a product like this, okay, I'm seeing, this, and that's it. No. Now, Ashley, my precious angel, brought me a going away present this morning. She brought me a Venti salted caramel mocha frappuccino. It's gone. I drank. The only thing I didn't drink in it was the whipped cream because I don't like whipped cream that much. But so I'm on like shots of espresso. Okay, so just keep that in mind. So we don't write this. We tell the grader, I understand this is a product, and I'm going to show you that I understand because I'm going to write out the rule mathematically. You see what I'm doing here? This is my next step. And then, or you don't even need to write that, just equals, right? And then e to the x plus e to the x, which is e to the x times x plus 1, something like that. All right, so you want to keep your work nice, neat, legible, compact together. Yeah.
So you don't have to copy down the f prime of x equals for each line?
No, you could just, so you need to state it once because that's proper use of mathematical notation. So, you get this function here, right? And you say, f prime of x equals, and you write out the rule, right? But after that, you can just use equals because this equals is following through from this. You see, it's very logically written. So no, you don't have to keep writing f prime of x. Now, when you get into BC and you start doing series, then you've got to write every little thing. And, it's a lot of work, a lot of writing in BC. So in BC, what's going to happen is in AB, you learn to become precise and quick with all the rules and apply them. And in BC, when you start dealing with the series convergence tests and whatnot, then you have to be very, very specific. So anyway, I hope that you get a teacher that's stricter than I am. So that way you'll all get 5s on the AP exam because that's the goal. Well, just to get you to pass the AP exam is really the goal. So anyway, just be careful with those things, all right? Because I know that those of you who are doing that, you know what you're doing. The problem is that you're going to lose points, all right? And failing to show work or showing the step that shows the greater that you know the product rule or quotient rule or whatever rule it is very bad, and you will lose points on that, and every point is precious on the AP exam. All right, so just keep that in mind. So let's go back into chapter, is it cinco? Is that the Spanish word for 5? Let's take a trip down memory lane. So we covered 5.1, which was increasing, I think. Let me just look here. I don't even know where this starts. Why is it like infinite? Here it is, chapter 5. So 5.1 was the increasing, decreasing functions. And that's very important because if you're given a function without a calculator, you're going to be asked, based on the derivative, what is the graph of f doing? Where is it increasing? Where is it decreasing? Is everybody okay with that? Everybody good with that? Crystal balls at home. I cannot read your minds.
Okay with it.
Yeah. Ariman, are you okay with this?
Yes, Miss Wilson, I'm okay with this.
Good. Mai?
I'm
You
good. Yeah, I got it.
Milana? Milana? Preksha?
Yes, I'm
You
good
good
with
with it? All right. So, and I know William is, so I'm not going to ask him. So in 5.1, we learned how to make these little wiggle graphs, right? To determine whether the graph of f is increasing or decreasing. We also learned how to algebraically find the exact critical points of the number. That way we could find maxes and mins, right? Local maxes and mins over or within a neighborhood. Yes? You learned the first derivative test, which is simply taking the derivative, setting it equal to 0, finding the critical numbers, testing on either side of the critical numbers to determine whether the function has a relative max or min. And if you're given endpoints, using that same idea along with the endpoints of the function to find the absolute extrema, correct? We're all cool with all of those things? This we skipped. All right. So I'm going to assume everybody's good then in chapter 5.1. So then we'll go to 5.2.
Miss Wilson.
Yeah.
Shri said she's in the waiting room right now.
Oh, okay. Let me let her in because we don't want anybody out in the cold waiting. Okay. So in 5.2, let me find, actually, I don't know why I scroll. 5.2, I believe, starts, no. So this is the part where Oh, by the way, I said this weekend I would upload all of the sections to the best book, and I'm almost there. I didn't get everything scanned yet, so probably tonight at some point I'll get all the sections uploaded for you. So the entire book, okay, including the entire Bob that goes with that. But in 5.2, let me open my book. We did second derivative, right? Finding inflection points using the second derivative test to determine local extrema. Any questions on that? Homework questions, any kind of questions on section 5.2? Done, go away, close. All right, then we're going to go into section 5.3 today, which is limits at infinity. Where we should be, actually. I just have to upload it from your Canvas course. And let's see, we are block 7. So let me grab that file real quick and load it up. So we want 5.3. Did y'all have a fabulous weekend?
Miss Wilson,
Mm-hmm.
can I ask questions on the chapter 4 test review, or is that?
That's fine. I would prefer to keep moving on, but that's fine. I can pull that up.
Okay. Could you go over number 17B?
17B. All right, let me find it. Hang on. 5.3. Okay, so for review, right? This one. 17B. Okay, so write the equation of a tangent line to the given curve, right? So your function, and I'm going to put this on another piece of paper. Let's hope I can, because you know how this works out. Copy and add a paper and paste. Yay, there it is. Okay, so we want to find the equation of a tangent line given this implicitly defined function. So remember that we're going to take the derivative of the function y with respect to x. So any variables that contain an x, when you take the derivative of those, it's going to be just like normally taking a derivative. But when you have a factor of y, that's where we're going to have to multiply the result by y prime or dy dx because we're taking the derivative implicitly. So taking the derivative here, we're going to have 6x plus, I'm going to pull out this 2. We're going to have x prime y plus xy prime. So I'm not taking a derivative here yet. I'm going to take the derivative of this one, which is 2y prime, and the derivative of the constant on the right is 0. Is that okay so far?
Yeah.
Okay, so now over here, I'm going to work on the derivative of what's left here. Well, we've got the derivative of x is 1 times y is y, plus the derivative of x times y is x y prime. Is that okay?
Yeah.
And now I'm going to go ahead and I'm going to multiply that 2 back in, and I'm going to get all of the y prime terms on the left and everything else over to the right. So 6x plus 2y plus 2xy prime plus 2yy prime is 0. And these are the two terms I'm going to keep on the left. And I'm going to subtract 6x and 2y to the right. And factoring out a y prime, that's going to leave us with 2x plus 2y is equal to the right-hand side. So y prime looks like it's this here. Now, we need a numerical slope and we need a point. Well, the point was given. The point is 1, -1, because we need to find the equation of the tangent line. So what I'm going to do is I'm going to plug a positive 1 in for x and a -1 in for y to get the numerical slope. So it'll be -6 times 1 minus 2 times -1 over 2 times 1 plus 2 times negative 1. If I clean that up, I'm going to have negative 6 plus 2 over 2 minus, ooh, really? Did that happen to all y'all's?
I got that, and as far as I know, like the actual book had an answer for this question, like an actual
does?
equation.
I wonder if I
So
made an error.
Miss Wilson, it works out because then you can just say that it's a vertical line at x equals
No,
1.
I understand that. I'm just shocked that he gave you one like that. Okay, so anyway, we get a 0 in the denominator, right? So we get negative 4 over 0. So what does that mean? Anybody?
Slope is undefined. So
Okay, it's undefined, but how are we going to write the equation of a tangent line with an undefined slope?
It would be your y is then your y coordinate, right?
I couldn't hear you. Say it again.
It would be like y, or like y equals your y coordinate, right? Like -1. Wouldn't that be your?
So remember when we have horizontal lines, right, with a 0 slope, we have y equals a number, like y equals to 2, right? And it looks like this. But how do we write an equation? So here's my axis, and let's just say, how do we write the equation of a vertical line? So remember, like if this were at x is equal to 1, we'd say the line x is equal to 1. So in other words, there's no y coordinate or y factor in there anywhere. So how would we write the equation of this tangent line? So I couldn't use y equals something, right? I mean, if you're thinking of the equation of a tangent line, it's y minus y naught, or a line is m times x minus x naught, right? But our slope is undefined. So what's going to happen? What did George write? Somebody said there was an answer there. What was George's answer?
it says x equals 1.
X equals 1. Interesting. Right. Because if I have something that's undefined times anything else, there's nothing there to do with it, right? I can't multiply something that's undefined to anything else. And by the way, if you think of this, if you divide both sides by m, you've got y, some y minus y naught over m is equal to x minus x naught. And so anyway, what I have here is I'm going to have y minus a -1 over some undefined slope, which would be 0 under here, is equal to x minus x naught. And so if I take this thing and I solve it, I'm going to get x is equal to +1. You will rarely see a problem like that, if ever. But what we need to do is go down memory lane with a little bit of algebra. This is very basic algebra that, again, it's very rare that you have problems like this, but I want you to remember that you're right, it's a vertical line, but the question is, how do we write it and why do we write it like that? And I'll be more than happy to make a little video or go over it, just not right now because I need to move on in chapter 5, because this is a prior knowledge thing that should be understood. So I'll do a little something on the side for you guys on that. But again, it's very, very rare that you're going to be dealing with something like this. But it's a good problem, actually. Now I like it. I just was shocked that he would give you one like that because it's so rare to see it.
Thank you, Ms. Wilson.
So you didn't have any problem with the derivative or anything. It was down here with the algebra, right?
Yeah, I forgot that if you don't have a slope, it can be a vertical line.
Yeah. The good old vertical line. All right, let's look at limits involving infinity because this is a big deal. And we're going to kind of use this extensively, right? And what I want you to remember is that when we're looking at limits infinity, we're trying to determine the end behavior of the function way, way, way out in positive and negative infinity land. We want to see what it's tending to. And there are reasons for it, and we can actually figure it out, even though we can't get to infinity to actually see what's going on there. All right, so let's look at the definition, because it's pretty important, as all mathematical definitions are. And the definition says a function f has a limit L, so some number, right? As x increases without bound, meaning going to positive or negative infinity, written as the limit as x approaches positive, and you can put a little minus under there too if you wanted to, positive and negative infinity, is equal to a number. If the outputs of the function, right, can be made as close to this limit as we like by taking x sufficiently large, meaning that our x values are going to get really, really big and really, really close to that value, but not at that value. So kind of the same definition as when x was approaching a number, a. It's just now we're going to positive or negative infinity. Okay, so anyway, if we look at this problem right here, you see now this limit here is going to negative infinity, all right? And this is very important down here, that the symbol infinity does not represent a real number, okay? And the symbols plus or minus infinity are used to indicate the behavior of the function outputs when x is really, really big or really, really small. Okay, so just kind of keep that in the back of your mind. And then this is something that I love to look at with the kids, because I usually start with 1/10 and I say, what's 1/10 as a decimal? And the kids say 0.1, and then we do 1/100, and you say 0.001. And anyway, the bigger this denominator becomes, if we're talking about this function 1/x, right? And we know what that graph looks like. In fact, it looks sort of like this, right? So what we want to know is, what's the end behavior as we go way out to infinity on the left and to infinity on the right? So as x gets really, really big, bigger and bigger and bigger, this thing is approaching 0. So while we can't walk out there to infinity land to really visualize it or see it, we know that we're taking values of x so big that we're headed toward 0 in both directions. And you know this because you have learned in the past, that the x-axis is asymptotic, right? The x and y-axis both are asymptotic for this particular function. So whether we go out to negative or positive infinity, we get a limit of 0. Is that okay? This is going to come in more handy. So this silly little example is going to come in more handy because you are actually going to have to show quite a bit of algebra in some of these problems as to how you get a 0 when you're taking a limit. And so here's what you're going to have to show, for example. So we have this limit as x approaches positive infinity. I can't just plug infinity in here for every x, because if I do, I'm going to get 1 plus infinity squared over 2 minus infinity squared. And infinity squared plus 1 is what? What happens when you add 1 to infinity?
Infinity.
You get infinity, right? And if you have 2 and you subtract infinity from it, you're going to also get infinity, but negative infinity here, right? And by the way, whether it's positive over positive or positive over negative infinity, if you ever cross those out and call that a 1, I will come from the depths of my home office and wring your necks. It is not 1. Infinity over infinity is not 1. You should know by now that that's something very special called an indeterminate form. L'Hopital's rule, ring a bell. So it does not reduce to 1, okay? Never ever in your wildest moment in life do that. Otherwise, I will die, okay? So what you have to do is show algebraically what's going on here. When this happens with a rational function, number 1, you need to take the highest, or let me say it this way. You need to take the variable of the highest degree from the numerator, or sorry, from the denominator. Number 2, you need to divide every term, top and bottom, by that x to the n, that highest degree variable in the denominator. And then you're going to simplify, and then and only then you're going to plug infinity in. I hate to use the word plug. And then you're going to find your limit. Okay. So in this particular example here, we have the limit as x approaches infinity of 1 plus x squared over 2 minus x squared. And what you need to do is look downstairs, number 1, and find the variable of the highest degree. Well, that would be x squared. I don't care about the sign. I just want the variable to the highest power. That would be x squared. And now what you need to do is say the limit. So hang on, let me do something here because I'm disturbed by his, because he uses every limit rule in the universe to do this, and you know, I can't deal. So you don't have to use every limit rule in the universe. You just need to show the work. So here's the function. So what you need to do is you need to say, you know, the limit as x approaches infinity. And by the way, if it's positive infinity, you don't need to put the plus sign there. But we determined that x squared is the highest degree of the denominator. So we're going to write every term up and down as divided by that denominator. And we're going to simplify it. So this equals the limit. You notice the limit notation is not going away. It needs to be there, of 1 over x squared minus 1 over 2 over x squared minus 1, right? At this point, I can't simplify it anymore, so we're going to plug infinity in. If I plug infinity in, that means I'm taking the limit, so the limit notation goes away. So what we have is 1 divided by infinity minus 1 over 2 divided by infinity. Infinity squares infinity, right? So minus 1. What's 1 divided by infinity? A ginormous number. What is 1 divided?
0.
It's 0. So we have 0 minus 1 over 0 minus 1. And a negative 1 divided by a negative 1 is a positive 1. So what we say is the limit as x approaches infinity of this function is equal to 1. Capiche?
So what I'm hearing is infinity divided by infinity did end up being 1.
Say that again.
What I'm hearing is that infinity divided by infinity still equals 1.
No, it doesn't.
But it just did.
No, it didn't. 0 minus 1 divided by 0 minus 1 is equal to 1. Bam. Next.
Miss Wilson,
Yeah.
you did, in the first step, you did 1 over x squared minus x squared over x squared, but the numerator is 1.
Oh, sorry. Oh, I didn't mean to do that. Hang on. I want my pen. There, right? Is that where I goofed?
Yeah.
Okay, so we have 1 over negative 1, so it's negative 1. Capiche? So you would actually on an FRQ have to show that work, okay? You must show the work. Oh, no, I didn't want to do that either. I didn't want to do it. Oh, here we were. So, yeah, so you see, this is why I wanted to skip his work. So you see, we got the same answer, so it's all good. But you see how he uses every, you know, this is a product, so we're going to raise a product. It's like a nightmare of epic proportions. So you don't have to do all of that, but you do have to show these steps, okay? All right, asymptotes. Yeah.
If on an FRQ the horizontal asymptote like if you don't need to show the work, like it's just like a part of the question, you can use the rules, right? Like the same over same and that stuff.
You mean if the degree of the numerator is the same as
Yeah.
the degree? Yeah.
Okay.
Right. And we're going to talk about that right now. Right. So a lot of times in calculus, you know, we're going to talk about vertical and horizontal asymptotes. And when you have a rational function, well, the vertical asymptotes are easy to find because you take the denominator, you set it equal to 0, and you solve, right? And that will give you the asymptotes that are vertical for the function. But for the horizontal asymptotes, you learned way back in algebra that if the degree of the numerator is bigger than the degree of the denominator, then there are no horizontal asymptotes. Is that right? Do you remember that, people? And if the degree of the numerator is less than the degree of the denominator, then you had a horizontal asymptote, which is the line y equals 0. Yes? And if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is the ratio of leading coefficients. And guess what? You can do the same thing in calculus. Okay, if you can remember these, then that's going to be a lot less work because most of the asymptotic questions occur as multiple choice. Not to say that you could never get one in a free response, but most of them are multiple choice. So let's see, what function do they have here? Oh, they have this one. So here they wanted you to find the horizontal asymptotes for this function x to the 4th plus x squared divided by x to the 4th plus 1. And you know, so far he's making these pretty simple examples here because we take the highest degree of the denominator and we divide up and down both sides by it, right? Every term. And what we get is 1 plus x squared over 1 plus x to the 4th. Plug our infinity in at this point, and we're going to get 1 plus 0 over 1 plus 0, which is uno, right? So what we would notice is that we would have, if we were to graph this out, we expect to see a horizontal asymptote at the line. Remember, it's a horizontal line, so it would be at y equals 1. That okay? But just knowing that the degree of the numerator is equal to the degree of the denominator, real quick, and say, oh, it's 1, right? 1 over 1 is 1. So having this little thing here way back from algebra is handy dandy because that can help you find a horizontal asymptote really, really quick in a pinch. What else is in this section? Vertical asymptotes, of course, if you had something like this function, you know, you would factor it down, right? X plus 1, and x minus 1. And so you say x cannot equal plus or minus 1 because you would know that you would have vertical asymptotes there, would make the denominator undefined. And for horizontal asymptotes, well, the degree of the numerator is less than degree of denominator. So we would expect to have a horizontal asymptote at the line y equals 0. Is that okay? And here's the graph so you can see it. So it's definitely asymptotic along the x-axis. Vertical asymptotes are here.
Sorry, can you please go back to the conditions for a horizontal asymptote really quickly?
Sure. If I can find them. There they are. So this is horizontal asymptotes. And I think these are really fun little problems to work on. They certainly help improve your algebra skills and complex fractions and things of that nature. And so the next section in the book, my darlings, is optimization, which is generally one of the most difficult topics in calculus. Now, not for all students, but for many, because y'all love word problems just so much. So I don't want to keep going unless you want me to, and I'll be happy to. But I would like the consensus. This is in a class of its own, okay? Limits at infinity. And you'll revisit them again down the road. But if you want me to keep going into 5.4, which is optimization, we can certainly do that too. So what's the, I don't know how to do polls and stuff like that on Zoom. I guess I better learn, right?
We can raise our hand. We can raise our hands.
Oh, yeah. All right. I never looked there, but yeah. So those of you who want to continue on into optimization, raise your hand. How do I know when your hand's raised?
You check the participant list.
Oh. Oh, how cute. Thanks, you guys. So 4 want me to go on. And it looks like the rest of you don't want to, and there's a lot more of the rest of you than are. So those of you who want to move on to optimization, raise your hand. If you don't want to, don't raise your hand. Ooh, 5. Ooh, we're almost at the halfway mark. Anish, you wanna do optimization. Be honest.
Oh, whoops. It looks like I'm unable to raise my hand.
Oh, you want me to raise it for you?
How inconvenient.
All right. Well, we'll make it an easy Monday since it's, what do you call that? Early release. And I'm going to have you do the following problems on limits of infinity, which will be due, when does our bell ring? At 11 something? When does our bell ring, William?
I think it's like 12:30.
Oh, all right. We have plenty of time then. Good. So this will be due by the end of by the bell. How's this for apples? You're going to do page 275, 1 through 19 odd. Due by the bell. Why? Because this is going to be an easy section. I will shut off my microphone. You guys can ask me questions for help. Maybe I'll even start working up that little explanation for you. And I'll make a video during lunch since I'm not hungry today because I drank that gigantic salted caramel thing that Ashley brought to me. Is Ashley in this class? No, she's in the next one, I think. Is Ashley in our class? Anyway. You hear, Craig? I drank a Starbucks.
I heard though, because I thought you hated it. And now apparently you like it?
Okay, so I don't hate the products from Starbucks. I hate the customer service at the Starbucks.
Okay, but then you're fueling their customer service by buying products, by spending.
I didn't buy it. That's just the point. And how could I be rude when she brought me first thing this morning before the bell even rang? What am I supposed to do? Say, no, I don't drink Starbucks. Here, take your drink back. No, I drank that baby to the last drop and it was divine. So anyway.
Well, real talk, Miss Wilson, are you actually going to switch to HBS or are you just going to become a full-time YouTuber? Because we all saw that video that you uploaded.
Yeah, I didn't mean for you to see it. Here's the story.
Man, I wish there was a video to teach me how to make quick, easy, and cheap biscuits, but I just can't find any.
So I made that a long time ago. I made it when Dr. Lynch was leaving. She's like, oh, I'm leaving and I'm not even going to get to say goodbye to anybody because, that's when we were in like the heat of the quarantine. So me and a couple other teachers said, well, let's meet at the school and we'll tailgate And I said, if I get up early enough, I'll make homemade biscuits and I'll bring some honey and whatnot. So I got up really early and I baked the biscuits and brought everything and made sure everything was like, social distance and paper plates and all that jazz. And they were like, oh my God, these are to die for. Can you tell me how to make them? And so I started telling them, they're like, no, can you make a video? So I'm like, sure. So I came home and pulled out all the stuff again and made another batch of biscuits. And I put the video up, but it was under private. Well, yesterday, my neighbors and I, we were all working in the front of our yards. And I said, you know what? Because we're such a cool street of people, I'm going to go in and make a country breakfast for everybody. So I went into my house and I made biscuits and bacon and all this stuff. And I went outside and passed out the biscuits. I'm like, oh my God, these are to die for. How do you make it? So I'm like, go to my YouTube channel. And I turned it from private to public. And then all of a sudden, a couple hours later, I go to my phone. I see like you have, 12 notifications. I'm like, what? For your biscuit recipe. And I started looking at the comments, and I don't even know what half of the comments meant, but I knew it was you guys messing up or playing around in there. So this morning I put it back to private. So that's the only reason I shared it, was for my neighbors. And who knew that the Middleton High School seniors would raise Cain with it? I have no intention of becoming a professional YouTuber. I think I'm probably the worst YouTubing person out there.
No, it was good. It was good. And Ella made an appearance. It was wonderful.
Ella? Yeah. Ella's always right there when I'm cooking. But anyway, yeah. So, my only goal on YouTube is to use it as a venue to help my kids. That's it. Have no intention or desire to become YouTube famous. So, yes, I am going to HBS next Monday. Well, I'm going home. I'll be home, but I'll be working there. But in the meantime, I'm trying to get things wrapped up here. Yes.
For when you're solving these algebraically, if like the highest exponent in the denominator has a coefficient, do we divide by the coefficient too?
No, that's a good question.
Okay.
No, leave the coefficient alone. Just divide by x to the whatever power it is. All right, now get your homework done because you have like 40 minutes or something. I'm going to mute myself.
It's a Monday.
Right.
What time does class end on Monday?
Like 11:30, William said. William said.
It's 11:53.
12:30.
Oh, 12:30.
Sorry,
Okay.
12:30.
Thank you.
Sorry. I'm looking up at the clock in front of me, which is an hour behind the time. You know how all my clocks are never on the same time or the right time? So, pardon me. Mahi, did you not show up to homeroom today or something, or to a class? Because you're shown as an unexcused absence in the system, just so you know. I'm not marking you unexcused, but that's what you're showing up as.
Me, Miss Wilson?
Yeah.
Oh, I'm not no, I was there in all my class. I don't know.
All right. Well, I'm just letting you know in case anything weird occurs as a result of it.
Okay, thank you.
Miss Wilson.
Yeah, sorry about the delay.
For one of them, I got once you substituted infinity and simplified, I got infinity over 1.
Which is infinity.
It's just infinity.
Right, and actually that's beautiful because when you get an answer of positive or negative infinity, we don't put that the answer is infinity, we say that the limit does not exist.
Okay.
All right, so whenever you get just plain old infinity, positive or negative as an answer, we say that the limit does not exist. That's the answer. Does not exist.
That goes along with if you use the rules like the shortcut, because it the numerator's degree is higher than the denominator's degree.
Right, there would be no asymptotes, no horizontal asymptotes. Which one are you working on?
Number 5.
Number 5. X squared over x plus 1, right?
Yeah.
Yeah, the degree of the numerator is bigger than the degree of the denominator. So what we know is that there would be no horizontal asymptotes. We have a vertical asymptote at x equals -1 by solving for the denominator. And but what they wanted to do, they wanted you to evaluate it, right? And so let's see. So at this point here, you're dividing by the highest degree of the denominator. So yeah, that would be the limit as x approaches negative infinity. If I divide, I'm going to have x over 1 plus 1 over x, right? And so it looks like it's negative infinity. Is that right?
Yeah, it would be negative infinity over 1.
Right. So we would just say the limit does not exist. So remember, this is the answer, not this. Not the answer. Robin, -60?
No. You mean plus 60? That makes more sense to me.
No, 60. And are you almost done with your work?
Almost is a subjective answer.
What number are you on?
It's definitely between 1 through 19. I'll tell you that.
You have to think about it. You can't specify?
Well, just give me some time and I'll get back to you. All right, come back to me.
Sure. Malav, what number are you on?
I just started 7.
7?
Yeah.
Okay, so Milana, what number are you on?
I'm on number 9.
Looks like Robin thus far is the only one with -60. Let me continue.
What do you mean? What do you mean? I'm on number 9. I'm on number 9.
No, you're not. Anish, what number are you on?
Nombre 7.
-40.
Seems legit.
-40.
Seems fair to me.
Yeah, you know how I am, right? By the way, did you guys look over your testises? I forgot to. I know I went over it in class, but did you have any questions or anything as to any of the comments I made or your score or anything like that? Okay, carry on.
Miss Wilson, are we able to use like
L'Hopital's rule?
Yeah, that one. Are we able to use that or?
So yes, you are. because definitely, the numerator derivative is 2x, the denominator is 1, you plug in infinity, you get, or negative infinity, you get negative infinity. So yeah, L'Hopital's rule, remember, we take the derivative of the top, derivative of the bottom. However, it's not part of this section, so guess what? You're not allowed to use it on a test. Make sense?
Yes, that makes sense. Thank you.
Yep, L'Hopital it. L'Hopital.
For 11 through 19, are we allowed to use those like 3 rules, or do we have to do calculus?
You mean like George Best would write it out? Is that what you mean?
Well, like it asks for the horizontal and vertical asymptotes. So
Oh.
are we, yeah.
No, you just use, degree of numerator less than degree of denominator. Yeah, use those. It's the easiest way. Now,
Yeah.
if you're taking a test, right? So the AP exam, I have to say this. You notice how they write in the function like in number 11, right? Is 1 over x squared, f of x, right? So you have to say, for the horizontal asymptotes, the limit, as x approaches infinity. So you would want to write that out of this function, but then use degree of numerator or degree of denominator. And anyway, what's the limit? Quick. 0, right? So in other words, you're going to have a horizontal asymptote at the line y is equal to 0. And then, of course, for the vertical asymptotes, you would specify VA or something, and you have x is equal to plus or minus 2, something like that. So make sure you use the limit notation as the point if you're taking the AP exam and it's FRQ. It's multiple choice, nobody cares. So let's see what's coming in the mailbox. Probably you have to proctor. Even when you leave, you have to proctor.
Miss Wilson, could you go over number 17?
Yeah. Robin just wants the answer, doesn't he?
I've been finished with 17.
You're finished? What's the answer, Robin?
Well, I mean, you're better at explaining, so I'll let you take the wheels here.
Not always.
Well, we'll see. I'll let you know if it's good when you're done.
Rule, right? We have chain. And so yeah, I want you to think about this very carefully. We know that the outer function, I'll just call it f, is ln x. And the inner function is 1 plus e to the x, all right? So if we just think about these two functions on their own, we know that the natural log graph kind of goes like this, right? And that in fact, that's kind of cool. The y-asic is asymptotic, right? The natural log cannot be negative, and it can't even be 0. Whereas the graph of e to the x plus 1, well, that's just the graph of e to the x shifted up 1 vertically. So, it's going to look the same, right? Like so. So the idea here is that, I know with ln x, and let me get my calculator too, because I want to show you something. Let me move. Guys, you should see the room. It's like a barren Like all my rugs are folded up. It's terrible. Oh, I have low battery. This is not cool because I don't have my well, I have my charger. I just don't know where it is. So let me try and show you this real quick before it dies. So I'm going to unshare this to get the camera up. All right, so if I grab, come on, hurry up, my calculator's gonna die. Hurry. Why are they coming? Oh. My camera's not on here, that's why. There we go. Let's focus it. Zoop. Okay. So anyway, if I graph this function, what I want you to notice is that the x-axis remains asymptotic to this thing. So the limit as we go to negative infinity is going to be 0. And as we go to positive infinity is going to be infinity. All right. So just keep that in the back of your mind. So you don't have degree of numerator divided by degree of denominator here. What you have to do is you have to think about this one a little bit. And for this particular composite here, and this would be a calculator problem, by the way, for AP, the AP exam. Your horizontal asymptote is at 0, and you would have no vertical asymptote. Right?
Okay,
To solve this is very, very difficult by hand. There are many that are unsolvable, or even many derivatives that don't exist, many antiderivatives that don't exist for functions. So, anywho, it's a beautiful thing. Madeline, you doing okay?
What did you say?
You doing okay?
Yeah, I'm doing okay.
All right. I know you're not like Robin or Anish or, so I was just checking though. Robin's probably playing a video game as we speak. And Anish is probably taking a nap. So
I would never, not in my favorite class.
yeah. Favorite class. What about Mrs. Knight's kids? Did she give you guys an assignment or anything like that? No. She didn't? Okay. What are you taking with her? Are you taking calculus? No? Pre-calc?
Ms. Wilson,
Yeah.
for 11 to 19, you said we could use those 3 rules, right? Instead of doing the algebraic method.
Correct. Uh-huh.
So then how would you want us to show our work for the vertical asymptotes?
For the last one?
Like it says horizontal and vertical asymptotes.
Right. So I kind of didn't hear what you said though a minute ago. How do you show work for what? The horizontal?
Yeah. For the vertical asymptotes, like what would you want us to show?
So for instance, like look at number 13, right? You have this function 4x over x squared minus 1. So you just say vertical asymptote, x is equal to plus or minus 1 because they know you're taking this and setting it equal to 0 to solve. So that's all.
Okay, thank you.
Miss Wilson?
Yep.
For the horizontal asymptote, if we're just using the rules, like, is there any differentiation between x approaching positive infinity and x approaching negative infinity?
Well, there could be.
Like, there's no way to figure that out with just the rules, right? With the rules, both of them are the same.
So like what problem are you talking about?
Like any of them, any of the ones we're using the rules.
So you're just talking about in general.
Yeah.
Well, right, because what's going to happen is when you plug infinity in, any number divided by whether it's positive or negative infinity is going to go to 0, right? So, you know, even if you think of something like this, I could write this as -1 over infinity, couldn't I? Oh, I'm sorry, you're not seeing my screen. Share the content, share the screen. There we go. Okay, so what I was saying is, you know, you could write 1 over negative infinity if you're plugging in a negative infinity as -1 over a positive infinity, right? Because negative a over b is equal to a over negative b, which is equal to the opposite of quantity a over b, right? So I can apply this negative sign anywhere I want. And -1 over infinity is still 0, right? So if you're dividing by infinity, regardless if it's positive or negative, it's going to collapse those terms to 0 regardless. Am I answering your question?
Yeah, I was just like, my question was basically like, if ever we had a function that had like a different horizontal asymptote for negative infinity and positive infinity, like we would have to, the only way we would find out is if we actually like did the whole method with the plugging in the infinity, because only then would there be a differentiation.
Right, so you have to take the limit, technically speaking. But if you know the little rules, like you were saying, then it's all going to work out okay. I'm trying to think. So like, for instance, e to the x, if we head toward negative infinity, we tend to 0, right? And as x goes to positive infinity, well, we're tending to positive infinity. So going in one direction does not yield the same limit as the other direction, which is why these are one-sided limits, either positive infinity or negative infinity, but not both. So if you use the rules, it's going to all work out. You don't need to worry about it, but you are going to have to show like the limit, you know, that you're taking the limit and you're dividing up and down and blah, blah, blah. Just remember that horizontal asymptotes can never equal infinity themselves because they're lines y equals some number, right? So it's y equals 10, y equals 20, y equals 1,000,000, y equals 5,000,000, y equals infinity. Could happen, but we would say that that doesn't exist. So I don't know if I'm answering your question or even if I understand it right, but if you use the rules, it will.
I was like, my base question was just, if you're using like the same degree over same degree and those three rules, there's no way that you can find like a negative infinity limit versus a positive infinity limit. Like they're both, it's just one answer, right?
Right, because well, what that's telling you is that whatever the function is, so I don't know, let's just say you had y is equal to 3x squared over, you know, 4x squared minus 1 or something. The degree of the top is equal to the degree of the denominator. So we know we're going to have a horizontal asymptote at 3/4, right? So what I know is whatever this graph looks like, if this is 1 here, we'll call, you know, this 3/4. This is going to be my horizontal asymptote. And whatever the graph looks like, whether it's going to positive or negative infinity, it's going to approach that asymptote height somehow horizontally. You see? So it's going to approach from in both directions is what I'm trying to say.
Yeah. If you had a function like the few functions that have different horizontal asymptotes and you use like the 3 rules to try and find them out, you would still only get one number, right? For both. Like that's what I'm trying to find. That's what
If
I'm
the horizontal asymptote exists, yeah.
Okay. So if you plug in the number, like that function into the 3 rules, you'd probably get does not exist if there were 2 different horizontal asymptotes, right?
Right.
Okay. Thank you.
Mhm. Because remember, lines are infinite, right? So we would expect, again, the end behavior on one could be 0, for instance, like e to the x, or positive infinity in the other direction. So it depends. We do still have a horizontal asymptote at y equals to 0 in this case right here. So there's a couple of, I don't want to say exceptions, but I'm going to call it that because it's for lack of a better word. There are some anomalies, but you don't need to worry about that. Nothing that you're going to do is going to be weird.
Ms. Wilson, is there a submission button for this?
There will be. I always forget to do that because I'm just so used to it automatically having one. Hang on, sorry. So we're in block 5, right? We're in block 5. And we have an assignment.
No, we're in block 7.
Oh, we're in blocks. Maybe that's why. Maybe I put it in block 5. Block 5 would be flipping out saying, oh my gosh, we just finished 4.3 today, or 4.4, and now she has us in block 5 or in chapter 5. All right, so yeah, there's nothing even there. So let me add that assignment for you. Section 5.3. Minutes at infinity. Is due today by 12:30. Robin, done. And it's going to be 10 points. Save and publish. Now hang on, because I got to go back in again and tell it to allow uploads. File uploads. Okay, so now it should be good.
Thank you.
Miss Wilson,
Uh-huh.
for 19, how would you go about finding the horizontal asymptote?
Hang on. Sorry. Number 19?
Yeah.
Yeah. So like this. You do have x in the bottom, right? And its degree is higher than the degree in the numerator, but you have a radical in your way, right? So what you can do is you can divide every term under that radical by x squared, okay? So what we're going to have is 2 over the square root of x squared over x squared minus 4 over x squared, all right? And this is going to be 2 over root 1 minus 4 over x squared. Actually, I don't know if I want to do it that way. Hang on. So a lot of times I'll factor out. Yeah. Okay, so let me show it to you this way. I'm doing essentially the same thing, but I'm going to factor out x squared. So I'm going to write this as x squared times 1 minus 4 over x squared. Is that okay?
Yeah.
All right. Now, rules of radicals say that if we have the product of two factors under a radical, then we can write those things in their own radicals, right? So I'm going to write this as root x squared times root 1 minus 4 over x squared. We cool?
Yeah.
Okay, so that's going to give me 2 over x times root 1 minus 4 over x squared. Now I can divide up and down by x. So I have 2 over x divided by x over x times root 1 minus 4 over x squared. Remember, this is a product, so I only have to divide what's outside by the x. Is that okay?
So even though it's like a product and the radical inside has an x squared, like the highest degree of the denominator would still be x.
Right. So I could pull out the x squared if you want.
No, I'm just asking, like,
But it's
even
not
if
going to matter, right?
Yeah.
No, I want you to see that. Right. So yeah, yeah, you can do that. So like this. All right. So what you really have here is 2 over x over root this. And if I'm taking a limit as x is approaching infinity, well, what do I get? I get 0 over the square root of 1 minus 0. So I get 0. That okay?
Wait, can you move your screen down a little bit? I can't really see the
Down?
Yeah, like no. So
This-
that like up,
wait,
I guess. is
Hang
better.
on, it's frozen. It's it won't let me because I'm at the bottom here. I'll hold it up like this. Can
No,
you-
that's enough. I can see it.
Okay. Was that her bell? No. Was that her bell?
No, it's only 12:25.
What would I do without you guys to keep me straight with my bells?
So for a problem like that, where like you can't really figure out right away what the degree of the bottom is, you would have to like take the limit of it. You can't use the rule.
Right.
Okay.
I mean, they would, so what I'm trying to say is if it's free response, they would expect to see this. It's multiple choice. You know, the degree of the denominator is definitely bigger than the degree of the numerator. And when that happens, we would expect a horizontal asymptote at y is equal to 0. And that's exactly what we got. So you wouldn't have to. But you know how I am about showing work, right? Because you never know what you're going to get on a free response problem.
So since the top is like there's no x, just the fact that the bottom has an x makes the bottom's degree higher.
Of course, because the top does have an x. It's 2x to the 0 over, you know, x squared, blah, blah, blah. So it does have a degree. It's just 0, and that's smaller than 2 or 1 if you factor out the x. So the degree of the numerator is smaller than or less than the degree of the denominator. Capiche? It's there, you just don't see it. So that's going to conclude limits at infinity until a further time. And so when I see you guys on Wednesday, we're going to do optimization problems. Remember the hiker in the woods and the boat out to the sea and open top boxes and all kind of cool area of rectangles that are moving between curves and whatnot. All of the fun stuff. Fun, fun, fun.
Miss Wilson, we should have a party on Friday.
Why? A virtual party? Like what we're supposed to
Obviously.
do, sit here? Will
Well,
says
I mean,
yes. Me and Will, I'll go buy cakes and Doritos and Will and I and pizza. Will and I'll have a party and you guys can watch us like eat. Sound like a plan?
Yeah, I mean we can get our own foods like from our for our own
And
parties at our place.
why should we have a party so you can celebrate my departure?
No, 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 not at all. A party to celebrate how awesome you
Going
are.
off on a good note.
Yeah,
Yeah,
exactly.
exactly.
Oh, well, you guys plan it all out and let me know what you come up with. But give me like 24 hours notice at the very least, because if we're really gonna have a party, then I do need to get some stuff.
We can play like Pictionary and stuff over Zoom.
Do you know how much trouble I'd probably get into? And it'd be my luck the
It's your last day. What are they gonna do? Fire you?
What?
I know.
True though.
No, they couldn't fire me, but I get nervous because you should be learning, right? That's the whole purpose of school, is that the students must learn bell to bell every day. And so I don't want to deprive you of that experience.
Are they gonna walk into class and be like, I don't see teaching activities going on, but you're just still on your iPad, still talking, still
Yeah,
drawing. They can't tell.
Birds might fly. Well, I project it on the iPad on the board for William.
Oh,
So he doesn't
okay.
have to be on his device if he doesn't want to be. So yeah, I've got 3 Zooms going. Noticed I'm the host 3 times because I have my iPad, the one on the board, the laptop, and the desktop. Anyway, let me know what you come up with. Have a great rest of your day, and we'll see you on Wednesday.
See you Wednesday.
Bye, William.
Bye, Miss Wilson.
See ya.
Bye, guys.
Miss Wilson.
Bye. The land of the mighty tigers.
Miss Wilson.
May your tigers be mighty and your homework be correct. You too.
Miss Wilson.
Thank you.
Yes, I'm listening.
Oh wait, I think Gayatri was first. You can go first.
Go ahead.
I was just gonna say that like I just finished it, so mine might be submitted at like 12:31 or 2.
Minus 60. No, I'm kidding. You're fine. Don't worry.
I had a question about for the assignments that I submitted when I was in block 8. I still have zeros for those. It's just like some of the COVID protocol and the first homework.
Oh, so I didn't transfer yours over. Is this a niche?
This is a niche.
Let me see.
It was the syllabus acknowledgement, the COVID protocol thing, and the section 2.2 homework. I submitted that all in block 8.
Hang on, let me just look at my grade, your grade in my grade book, and then I'll fix it so I don't forget. So Anish is here. So yeah, so that's a 10. The 2.2 homework you said, and the
Yeah.
yeah, okay.
Yeah, and the 2 forms, the syllabus and the COVID protocol.
It's fixed.
Okay.
Thanks.
Thanks, Ms. Wilson. Have a good day.
You too. Bye bye.